All right, since that last one kind of ended in a disaster, let's see if we can fix it on the next one. Um, I would try this on your own before I work this for you. The equilibrium constant is 2.6 times 10 to the negative third. I like that because that is small for this equation. If 0.312 moles and 0.013 moles of N2 and O2 are mixed in a 1 liter container, I like 1 liter. I like that a lot. I also think on that last one they assumed 1 liter and it said 750. So I'm convinced I did it right. Anyways, this one will actually match the answer key. I was right. So I have 0.312 molar, 0.312 molar, and I've got 0.013 of both of these. So I'm starting with something on both. 0.013, 0.013. So this is going to be minus 2x plus x plus x. So I'm going to have 0.312 minus 2x, but we know that the x is going to 0. 0.013 plus x, 0.013 plus x. Am I recording? Yeah, okay, good. Excelente. So let's set that up equal to k. So 2.6 times 10 to the negative third equals 0.013 plus x. That whole thing is going to be squared. Divided by 0.312 minus 2x. That whole thing is going to be squared. So the first thing we're going to do is take a square root of both of those things. I'm going to square root this. I'm going to square root this. So what is the square root of 2.6? Negative third. 0.051. So 0.051 equals 0.013 plus x over 0.312. I'm getting rid of the 2x because that went to 0. Multiply across, solve for x, and let me make sure, 0.312 times 0.051 minus 0.013, 0.0029. So x equals 0.0029. So what are the concentrations when it's reached? So I'm going to have 0.013. Oh, wait a second. Yeah, 0.013 plus 0.0029, which is going to be 0.013 plus 0.0029. Gives me 0.0159. So N2 equals O2, which equals 0.0159 molar. And NO2 is going to be 0.312 minus 2 times 0.0029, 0.307. 0.307 molar. So there's some ice table review. Kind of nice. I know what happened here. It's because they forgot when they made this answer key it was 750. I did it right. I know you guys would do that right. In the boxes below, create a particle diagram that demonstrates the reaction for each equilibrium constant. Represent reactants as solid and product as empty. Okay, we get it. All right. 1, 2, 3, 4, 5, 6. K equals 1. Equal. K is less than 1. Let's stick with the 6. 1, 2, 3, 4, 5, 6. I have to have 1, 2, 3 more reactants than products. And if K is greater than 1, 1, 2, 3, 4, 5, 6, I'm going to have more, so reactants must be less than products. Determine how the equilibrium constant for each particle diagram you made above. Oh, determine the equilibrium constant. Each container is 1 liter. For each circle that you drew is 0.5 moles. Okay. That's weird. So based off of mine, each circle you drew is 0.5 moles. So I have 1, 2, 3, 4, 5, 6. So that's 3 moles divided by 1 liter. So, 3 total moles. So I have 1.5 moles of reactant, 1.5 moles of product. Okay, C equals 1. Imagine that. On this one, 1.5 molar, I'm going to have, for reactant, I'm going to have 2. Product, I'm going to have 1. So this one, my K equals 1 divided by 2. So 0.5, which makes sense. And this one, I'm going to have 1 mole of reactant, 2 moles of product. So 2 divided by 1 equals 2. So yeah, we're just proving K. The particle diagram shows that reaction AB yields AB at 0 minutes. Determine the Q value at 10 to 30 minutes. Use the provided information to draw the appropriate particle diagram and calculate Q or K. So we're going to have to follow law of conservation of matter. So at 0 minutes, I know that Q is going to equal 0 products over 5 reactants. So Q is 0. This one, we're saying that Q is equal to 1 times 1. Ooh, snap. So I'm going to break up 1. So let's break up 1. If we're going to show a difference here. So 1 solid, 1 dark. And I'm going to keep the 4 together. 1, 2, 3. Does that mean 1, 2, 3, 4, 5? 1, 2, 3, 4, 5. So I have 1 of each of my products. I have 1 product, 1 product. 1 divided by 4 is 0.25. Okay, now they want 3. So I'm going to break up 3 of them. So 1, 1, 1, 1, 1, 1, dark, dark, dark. That leaves 2 together. So 1, 2, 1, 2. 9 over 2 is 4.5. My K is getting larger. This was 0.25, by the way. And at 30 minutes, I'm going to make my K, let's see. At this point, I have to hit equilibrium because I can't really make it anymore. So I'm going to keep this at equilibrium. So K would have to equal 3 times 3 over 2, which is going to equal 4.5. So this should be the same. So I'm going to have 1, 2, 3, 1, 2, 3, 1, 2, 3, and then still my 2 that are together. How do I know at 30 minutes it hits equilibrium? So this is saying that AB yields A plus B at 0 minutes. So I know that this is not going to go to completion. So because it's not going to go to completion, at this point, it's kind of a big assumption here that it's going to stay at equilibrium, but that's what they're going for. All right, let's flip it. That was, in all honesty, kind of annoying. That's okay. To restore equilibrium, here we go, Le Chatelier's principle. A reaction will shift away from the side that has been added something to. To restore equilibrium, a reactant will shift toward the side that has something removed from it. To restore equilibrium, an increase in pressure, aka a decrease in volume, will cause a shift to the side with the less amount of moles of gas. To restore equilibrium, a decrease in pressure, aka an increase in volume, will cause a shift to the side with the more moles of gas. It's the opposite of what we just said. So heat applied to a blank reaction will cause a shift towards the reverse. That's going to have to be an exothermic. Why? Heat is a product. Heat is a product / released during an exothermic reaction. Particle diagram represents the reaction. A3B yields 3A plus B. Draw an approximation of the particle diagram after reaching equilibrium in a container with a greater volume. This is going to be difficult to show. So if I'm at equilibrium, I have to have equal reactants and products. So I have, let's see, I'm going to have some kind of, I'm going to have at least one of these. So draw an approximation of particle after reaching equilibrium. So if I broke up, let's try 4. 1, 2, 3, 4. If I have 4 floating around, that means I broke up one particle. So that means I'm going to have at least one particle together. So 1, 2, 3, 1. There's one together. Let's see my law of conservation matter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 1, 2, 3, 4, 5, 6, 7. I have 4 possible left, but I need to make this equal to 1. So how am I going to do this? Let's try it with another one. If I did this, if I drew with 1, 2, 3, with another one that stays together. So 2 are staying together. So 2 are staying together. I broke up 1. How many white circles do I need left? 1, 2. I need to have 2 of these. So that would give me, for products, 4 times 2, which is 8 over 2. That would give me 4. Oh, shoot. But I have to I have to consider my actual equation here. So if this was it, I would have I would have 4 cubed times 2 over 2. Let's see what that would be. Oh boy. 12, 24, that'd be 12. So I have way too many products here. So if I put one of these back together, reactants over products. Products over reactants, so it would be 4. Did I follow the law of conservation matter? 3, 6, 10, 3, 6, 9, 12. I did not. That's why, because I didn't account for those first 3. I already had some to start. What if we just break up 1? So if that's not there, and I just break up 1. So I would have 1. Oh, that's what I did that time. No, I should still have 2. If I break up 2 and I only have 1, I have to reach in equilibrium. I need to think about this once. I don't know why I am getting flipped up on this. This is unit 7. This is so weird. This is what happens when you are using a thing that you did not make. I just want to make sure I'm not messing up here. but I think I need to leave 2 together. So if I leave 2 together, yeah, I think I had it right actually. So 1, 2, 3. Wow, I'm not drawing this well. Circle, 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 white circle. So I have 1, 2, 3, 4. 1, 2, 3, 4. That's nothing. I have 1, 2, 3, 4. So I have 3, 6, 10. 3, 6, 9, 10. I need to have 2 more of these. That's just about the closest I can make it. So that means for A, I have 2, 4, 6. Yeah, there's really no math to do this. After reaching equilibrium, this is the closest I can get. Because if I'm starting with 3, I can either go to... Yeah. We're doing this conceptually, that's my bad. If I'm starting with 3 of my reactants, if I'm not going to go to completion, I can't have 0. So I just have to delete one of these, just break one of them up. So ignore this, ignore this. I broke up one particle. That's closer to equilibrium. Wow. I really made that hard. Don't do that on your AP test. Consider the reaction C plus D is equilibrium with EF. How would the concentration of each species be impacted if you increase the pressure on the system? Well, it gives me literally no states or no moles. And it's also 1 to 1 to 1 to 1. So the answer is none. That was easy. Sorry I overthought this. Just to explain this one more time, I have 3 molecules of reactants. It's not going to go to completion. So the only thing I can show is 1 less reactant to make it close to equilibrium. So I got rid of 1, broke up the other one, and that's what I ended up with. Ignore those big scribbles. Okay. All right, we got some shifting. This is the fun part. You're observing the following exothermic reaction, exothermic, so I'm going to write plus heat. A is red, B is yellow. So I have red, I have yellow. At 25, it's orange. Predict what will happen to the color as you change the temperature. So at 10 degrees, I've removed heat, which is going to shift it towards the products. So that is going to be more yellow. Does K increase or decrease? More products. So K is going to increase. If I increase the heat, that's going to shift it back to the reactant. So it's going to be more red. And that's going to cause my K to decrease. Endothermic, going to be the exact opposite. So plus heat, I have F is yellow, G is blue. So if I decrease the temperature, it's going to shift towards my products. So that's going to be more yellow. My K is going to increase. If I increase the temperature, it's now going to shift towards the products. It's going to be more blue. It's going to be more blue, which is going to make my K... Wait a second. This one was shifting towards the products. This K should have went down. This one's shifting towards the products. This one should have went up. I flipped that. That's my bad. Finally on this side, the reaction B, equilibrium with C is equilibrium with 1 plus. B is a red gas. What will happen to the color in the beaker if it's put under greater pressure? Well, it's going to shift to the side with the least amount of moles of gas. But the thing is, this is a solid. So either way, it's going to turn to more solid and less gas. So it's going to be less red. It's going to be less red because it's going to shift towards the products. It's going to become more solid, less gas. Okay. Looking over here, and once again, I'd try to do this on your own quick. I'd pause and do this on your own really quick. NO2 is added. So if I'm adding in reactant, then product is going to increase. Product is going to increase. I add in product. My reactant is going to increase, and my products are going to decrease. If I add in product, again, this is kind of repetitive, but that's okay. Increase, my other reactant is going to decrease. If I remove NO2, then that means that it's going to shift back to the reactants, which means the products are going to decrease. Wait, if I remove NO2, if NO2 is removed, that means that these are going to decrease. So decrease, decrease. If NO is removed, if I'm removing product, it's going to shift back to that side. So increase, increase, decrease. If I remove O2, that's another one, so that's going to be the same thing again. So this is going to be decrease, increase, increase. If I increase the temp, this is endothermic, so plus heat. So that's going to shift it to the right, which is going to decrease my reactants, increase my products. Decrease is going to be the opposite, so up, down, down. Then lastly, increase the pressure. It's going to shift to the side with least amount of moles of gas, so I have 3 on this side, 2 on this side, so it's going to shift towards the reactants. So increase, decrease, decrease. Decrease the volume is the exact opposite as increasing the pressure, so it's going to be decrease, increase, increase. That was a lot of Le Chatelier. 710, here we go. Lastly, complete the following chart. Will K change? You increase the temperature. So, what will happen to the equilibrium constant and the reaction quotient immediately after the following? Increasing temperature is the only thing that affects K, so yes. Increasing the pressure. So what will happen to the equilibrium constant and the reaction quotient immediately following the address stress? Increasing the pressure, K will not change. Increasing the concentration, K will not change. K only changes with temperature. But what happens to Q? So Q has to shift towards the new K on this one because K actually changed. On this one, Q changes. So all 3 of these are going to be Q changes, Q changes, Q changes. Following reaction is allowed to reach equilibrium. Then the pressure changes so that PNO is 0.72, 0.025, 0.34. Calculate the QP, explain the reaction, and proceeds. So I have to do a Q expression. So Q equals NOBR. That's going to be squared over NO. That's going to be squared times BR. So Q equals NOBR is 3.4. So that's going to be squared over NO, which is 0.72. That's going to be squared times BR, which is going to be 0.025. Multiply that out. Q equals 892. Therefore, I would say that Q is definitely greater than K, which is wrong. So it shifts to the left. So it shifts left. Based on your knowledge of Le Chatelier's principle, when the pressure was changed in the reaction, was the pressure increased or decreased? Explain how you know. Well, I increased the pressure. My Q went up. So that means that there was more product than K required, which is more moles of gas. So that means that the pressure must have actually decreased. Because if it shifts left, it's shifting to the side with the more moles of gas. Shifting to 3, it's supposed to shift to the left, so that's the opposite. So pressure decreased. Okie dokie. We are almost there. Oh my gosh, we're not almost there. This might have to be a 3-parter. Draw a dotted line to mark the moment when a change in the reaction happened. What was the change? So, a dotted line. Here was the change. Here was a change. Here's my reaction. So what changed? My AB2 went down. So what I did is let's see. My AB2 went down. Oh, how many of these do I even have? I think I removed AB2. I removed AB2. When I removed AB2, it shifted back to this side. So it started going back up, and these went down. On this next one, at 10 minutes direction to the left, experience an increase in pressure. So that means it's going to shift to the side with the least amount of moles of gas. So it's going to shift to the left. So it's going to shift to the left, which means my AB is going to go down. My B is going to go down, and my AB2 is going to go up. This next one is 10 minutes of stress is added to the system that causes K to increase. This is just like our straw lab that we did. Continue the line for each species to describe what happens as the concentrations so a stress is applied to the system that causes K to increase. If K is increasing, that means my products have to go up. So product going up, product going up, reactants have to go down. At 5 minutes, more AB2 is added to the system. What will immediately happen in the reaction? So if this is my reaction, I am going to go up, and then it's going to immediately start being used up again. So there's some kind of graphical K expressions. Then we're going to move into some solubility, KSP. So solubility is defined as the amount of solute that will dissolve to form a saturated solution at a particular pressure and temperature. So use the information for the following questions. Calcium hydroxide has a KSP. Iron hydroxide has a KSP of this. Write the dissolution expression for each. So if you guys remember how to do these, CaOH2 is in equilibrium with Ca plus 2 plus 2OH minus. On this one, so that's my expression. The KSP is going to equal the concentration of just the ion, Ca plus 2 times OH minus squared. Because remember how it's like the x or the 4x cubed? That's what we're doing here. So there's my expression. Anything else I need to do for that? Oh, I guess I have to do it for the other one too, on the same line. So iron 2 hydroxide, so Fe, I don't know why they didn't make something a little bit different, but it's fine, we'll do it. Fe plus 2 OH minus, and for this one, KSP is going to equal concentration of Fe plus 2 times the concentration of OH minus squared. Which salt is more soluble? Did they give us KSP? Oh yeah, here we go. -6, -18th. CaOH2. How do I know? Higher KSP. Which salt has a stronger intermolecular forces? Well, it's going to be iron. Wait a second. It's more soluble. Stronger intermolecular forces with the solvent. Oh, which has stronger intermolecular forces with the solvent? That's going to be CaOH2. Because if it dissolves well, that means it has stronger interactions, which means it likes it. That's that like dissolves like, which we don't want to say. We want to say stronger interactions with the solvent. This is why water dissolves salt, because water is polar and salt is polar. They're both ionic. They're both, I mean, I guess water has hydrogen bonding, but there's still a dipole moment in both of those. You have two flasks of equilibrium. One has calcium hydroxide, one has iron 2 hydroxide. Which flask has a higher concentration of ions? CaOH2. Once again, why? higher KSP, so more are going to dissolve. You allow solvent to evaporate from two flasks, increasing the concentration of ions in each. Which salt would precipitate first? How do you know? FeOH2 is going to precipitate first. Why? Lower KSP. Therefore, it is less soluble. So fewer ions can still be held in that solution. I'm trying to figure out if we're going to finish this. I'm also waiting for the plumber to call me. The plumber has not called me. Oh, we are so close. We're just going to rock this. We're going to finish it. Why do solubility expressions not have denominators? Well, the denominator is always going to be the solid. It's something dissolving, so the reactants are solid, not part of equilibrium. Which of the following are true or false? When a solution in equilibrium, the concentration of dissolved solute remains constant. True. When the solution is in equilibrium, the solid salt is always completely dissolved. No. Why does it have to be completely dissolved? It could be partly dissolved. False. Write the dissolution equation for the dissolution of AgI. You have saturated solution of AgI in a 1 liter beaker. Calculate the I concentration if Ag is 8.8 and KSP is 8.5. So here we go with the math of this. So I have AgI is going to be in equilibrium with Ag plus 1 plus I minus. And they are telling me the KSP for this would be Ag times I minus. So this means that they gave me the KSP. 8.5 times 10 to the negative 17th equals, they gave me Ag as 8.8 times 10 to the negative 7th times I. Solve for X, and you should end up with 9.7 times 10 to the negative 11th molar equals the concentration of I minus. Over here, this is going to be, let's see, a little bit different because I have BaCl2. So that means that KSP is going to equal Ba plus 2 Cl minus. Because I wouldn't have written out the equation, I'll write it. BaCl2 is going to break up into Ba plus 2 Cl minus. So on this one, KSP, they gave me both of these. So the saturated solution is 0.75 molars. Determine the concentration of each ion in saturated solution. Calculate the KSP. Well, if the concentration of the saturated solution is 0.75 molar, determine the concentration of each ion in the saturated solution. Calculate the KSP of the BaCl2. So I'm going to have to assume that the Ba is 0.75. So if this is 0.75 molar, that means that my Cl2 has to be double that. So this is going to be, that should not be plus, by the way. This should be multiplied. It's really late on Friday, guys, when I'm recording this. Like, it's way after I should have been here. 0.75 molar, so that means the other one has to be 2 times 0.75, which is 1.5 molar squared. So KSP equals 1.69. And then it, of course, split this ice table up onto 2 pages. So what I'm going to do is make this I, make this C, make this E, so this actually works. So I have Mg plus 2 and 2F minus, if I'm breaking this up. Initial concentration, what are the concentrations of these? So I have nothing because it has to dissolve. My change is going to be plus X. My change is going to be plus 2X. So this is going to be X, and this is going to be 2x. And they tell me the KSP, what are the concentrations? So this means that KSP equals x times 2x squared. So KSP equals 4x cubed. And they gave me the KSP, which is 5.16 times 10 to the negative 11th equals 4x cubed. Solve for x. And you are going to end up with 2.34 times 10 to the negative 4th molar. So that is going to be the answer for your x. So the answer is find all of your answers. So I have MgF2. It's a 1-to-1 ratio between MgF2 and the Mg. So if I would have written out this equation, MgF2 is in equilibrium with Mg plus 2 plus 2F minus. Because this is 2.34, so is that. So the molar solubility is that, and then this one would be double. Easy. There's the E. That's so silly. Put together 3 pairs of salts that would experience the common ion effect if dissolved in the same solution. Okay, well, if I did BaCO3, that would form a common ion with CaCO3. There's my common ion. If I do CaC2O4, that would form a common ion with CaCO3. There's my common ion. Last one, PbBr2, PbCl2. There's my common ion. Here we go. You have a saturated solution of sodium chloride dissolved in water. What will happen to the Q, KSP in each situation? Increase, decrease, stay the same. Add AgCl. So that means it's going to be adding more chlorine ion. So if I am going to write this equation out, NaCl is in equilibrium with Na plus Cl minus. I'm adding in Cl. That's going to shift it to the left. So that means that Q is going to decrease. I add in CaCO3. That's not a common ion, so nothing. What happens to my K? Remember, the temperature stayed the same. So K is the same. None. Go on to the next page. Because my Q, because I am shifting to the right, that means my Q is going to form more reactant. So it's going to, because it is shifting to, my QSP is going down, it's shifting to the left. So to reach equilibrium, I have to shift left. Solubility of the NaCl is going to go down because it's shifting left. And this is still none. None. Sorry that did not copy well, everybody. Oh my gosh. I'm going to have to call it there, and we're going to do a mini part 3 because I really have to go home and pick up my daughter. Part 3. Stay tuned.